Okay, so at this point in time, you should be able to list the three subatomic particles. Recall that the three subatomic particles are protons, which have a positive charge, neutrons, which have no charge whatsoever, and electrons, which have a negative charge. For all three of these, you should also know the relative weights of them. Protons and neutrons both weigh roughly the same amount, being 1 atomic mass units. Atomic mass unit is simply just our general weight for all of these things. And electrons are so small and light that we basically consider their masses to be 0. So their masses are so infinitesimally small that they have an atomic mass that is considered as negligible. This is AMU, by the way. That stands for atomic mass unit. Now then, recall that every single atom is comprised of the three subatomic particles. The existence of those three in different quantities is what makes every single element unique. Now, using the periodic table, we're actually going to be able to determine every single one of these values for every single element on the periodic table. Now, this is typically what an element on the periodic table is going to be listed as. As you can see, we are working with carbon. The symbol for carbon is the letter C. Now, the first number that we're going to talk about is the atomic number, which is the top number that you see right here. Now, what the atomic number literally describes is simply the amount of protons that that atom / element is going to hang on to. So when looking at carbon, because it has an atomic number of 6, you can essentially say that it has 6 protons. Simple enough. So every single carbon atom is going to have 6 protons due to that being the atomic number. Now then, if you were to say look at any element on the periodic table, you would find that they are all considered to be in a neutral state, which means that they all have no charge whatsoever. Now, because carbon has 6 protons, that means it needs an equivalent amount of electrons in order to balance out those 6 protons. So whenever you're looking at the periodic table, you would essentially say that the number of protons will be equal to the number of electrons. So as it stands, we know that carbon has 6 protons, and it must have an equivalent amount of electrons. So it also has 6 electrons. Now, there's another number that every single element has when you view it on the periodic table, and that is the mass number, which is the bottom number. You can always tell the difference between the atomic number and the mass number simply because the atomic number is just one simple integer, versus the mass number, which is always going to be decimal places on decimal places, and it will be a very precise number. Now, the mass number is exactly what it sounds like. It will tell you the mass of an atom per mole of that atom, or you can basically say that it's the mass of one atom of an element. The units that we're going to be using are grams per mole, but more specifically in this section, we're going to focus on AMU, or like previously stated, atomic mass units. Now, because we had previously stated that protons and neutrons are the only subatomic particles that actually have a mass worth caring about, the summation, or the sum of the protons and neutrons, will be equal to the mass number. Remember that electrons are considered so light and having such a small weight that it's basically considered negligible. So the weight that protons have on an overall element will not be factored into calculating the mass number. And so what that means is that when we're calculating for mass number, you would basically say mass number is equal to the number of protons plus the number of neutrons. The really, really awesome thing is, assuming that you have a periodic table on hand, you always have access to 2 of these values. First of all, you always have the mass number because that's the bottom number that you see right here. And in addition to that, you always have the number of protons, because remember, the atomic number tells you the number of protons that an element is going to have. So we can actually figure out, with all of the information given to us, the amount of protons, electrons, and neutrons that a singular carbon atom holds. We had already stated before that since the atomic number of carbon is 6, that means it has 6 protons. Since it has 6 protons, it's going to need an equivalent amount of electrons to balance out that charge. And lastly, we just need to solve for the number of neutrons using the mass number equation. Because remember, mass number, which is going to be 12, is equal to the number of protons, which is 6, plus the number of neutrons. We can rearrange this equation, or you can just subtract the mass number by the number of protons to get the number of neutrons. 12 minus 6 is 6, so carbon also has 6 neutrons. And if you really wanted to, you can verify this answer by just adding up your protons and your neutrons. If the protons plus neutrons gives you a number that's equal to the mass number, congratulations, you did it right. Next up, we're going to go ahead and talk about isotopes. Now, isotopes are the same exact elements, but there's a slight difference. So in nature, you're going to see various forms of the same exact element. We're going to talk specifically right now about carbon-12 versus carbon-14. Now, carbon-12 and carbon-14 are both carbon atoms, so they both will have an atomic number of 6. However, the main difference between the two has to deal with their masses. So carbon-12 is going to weigh 12 atomic mass units. Carbon-14 is going to weigh 14 atomic mass units. Now the reason why they weigh different amounts is because they are isotopes of one another, or simply they have differing amounts of neutrons. So isotopes are atoms of the same exact element that will only differ in the number of neutrons. Due to the number of neutrons changing from one isotope to the other, that means that the mass of both of these is going to be slightly different. And as previously stated, carbon-12 or C12 will have a mass of 12 grams per mole, or atomic mass units, and carbon-14 or C14 will have a mass of 14 grams per mole, or 14 atomic mass units. Now what we can do is we can actually solve for the number of protons, neutrons, and electrons in both of these. Recall that carbon has an atomic number of 6. So when looking at C12, you would say that it has 6 protons. Carbon-14 is still going to be carbon, and every single atom of carbon has an atomic number of 6, which means that carbon-14 also has 6 protons. Carbon-12 needs to have 6 electrons in order to balance out the charge of the 6 protons, as does carbon-14. It's going to need 6 electrons in order to balance out the charge of the 6 protons. Now this is where they begin to differentiate with one another. Carbon-12 has a mass of 12 atomic mass units. In order for this to have a mass of 12 atomic mass units, you need to have 6 neutrons. Because remember, the atomic mass is equal to the number of protons plus neutrons. 6 plus 6 equals 12. Carbon-14, however, is going to weigh 14 atomic mass units. If you were to say that it had 6 neutrons, that would not end up equaling to 14 atomic mass units. Carbon-14 in reality has 8 neutrons. And if you want to verify that, again, just simply add up the number of protons and the number of neutrons. 6 plus 8 is 14, which means carbon-14 has this many neutrons. Notice how the number of protons stays the same, the number of electrons stays the same, the only difference is the number of neutrons. The difference in the number of neutrons inherently changes the mass of both of these isotopes. As a quick disclaimer, you cannot change the number of protons when talking about isotopes. If you were to change the number of protons to, let's say, 7, you're now dealing with the element that has an atomic number of 7. So once you go up to 7 protons, you're no longer dealing with carbon, you're dealing with nitrogen. And remember, for isotopes, it has to be the same exact element. So nitrogen and carbon-12/14 are not isotopes of one another. In addition to that, you cannot change the number of electrons to form isotopes. Isotopes need to have differences in mass. And as previously stated, electrons have a mass that is basically equal to 0. So you can add up as many electrons as you feel like it. You can even bump this up to 30 electrons, 100 electrons, infinite electrons for all that matters. The mass of this entire molecule will never change because we consider electrons as having a negligible mass. The only way to change the mass while retaining the same exact element is by changing the number of neutrons. Okay? That will do it for today. Thank you for listening.